Welcome back. Today is October the 26th, and we're going to continue here in chapter 8. And we're going to be talking about the Diels-Aldrich reaction. All right, the Diels-Aldrich reaction is a Nobel Prize winning reaction, and it's known as the 4+2 cyclodation because it involves 4 pi electrons on the diene and 2 pi electrons on the dienophile. All right. And so I'm going to teach you today what I call the right approach, the 3D connection, and the 2D product. It could be an endo or it could be an exo product. So we're going to learn those terms. And I want you to use this practice to be able to solve the problems that will be given in the milestone. There are 3 things about the Diels-Aldrich. You can predict the endo product, you can predict the exo product, or if I give you both of those products, you can predict the starting materials. All right? And so those sigma bonds that you make, you need to break them to go back. That will be your retrosynthetic analysis. All right? Very common. Most books and electronic homeworks like Pearson, they quiz students that way, going forward and also going backwards, all the way to the starting materials. So I want you to get good at both. All right. So here we go. The first thing that you want to do in the Diels-Aldrich reaction is finding the most electron-rich carbon on the diene. All right? So that's the first thing. You can take notes if you want, write that down. But that's your first task. All right, so if you look at my diene here, I will purposely put this lone pair of electrons because I need them. And so I'm going to push electrons with this nitrogen. I'm going to push electrons here, here, and I get all the way to here. All right? So that will be the resonance structure for that. But I'm not going to draw any resonance structure. I'm just pushing electrons to see where they will flow. All right? Then I'm going to switch pens. I'm going to do the same thing with this oxygen. I'm going to go there and here. And notice that means this carbon right here is my electron rich. All right, I'm going to delete that because I need space. So then, according to this model, you will know that this carbon, the electron-rich carbon, should end up at 6 o'clock. Hold on a second. Let me wait for this to populate. Yeah, if I have a clock here, and this is 12, 3, 6, and 9, my electron-rich will be right here at 6 o'clock. And this will be my electron rich, and my electron poor will be at 4 p.m., roughly around 4 o'clock. All right. So basically, you will see this in a minute. So just keep that in mind. This is my electron poor. So this is going to be the diene, and right here will be the dienophile. Oh no, there's some glitch here. All right. Okay. All right. So let's get done with this. All right. So basically what we will see is that if I label the diene in purple is going to connect with the dienophile here in green, and we will have a bond there.
I don't think we can see what you're trying to show.
No? Yeah, in a minute you'll see.
Okay, sorry.
Yeah.
Are you showing over there? My bad.
Yeah. Oh, yeah.
Sorry.
Oh, you didn't see it from this?
No, yeah, no. I just didn't notice you were drawing over there. That's my bad.
Oh, okay, sorry. Yeah, that's the thing, because I need to be right on top of this computer in order for me to teach my online students. So kind of my in-class students kind of lose, that interaction with me with the board, which I hate it because I miss it too. Anyway, here, and I apologize for that. So I'm going to start here with my diene. So I'm going to put it on the top. I'm on top of what it looks like a box, right? So then I noticed that my methoxy group will go here on this carbon. You see it, right? And the dimethyl amino group will be there. You can type the two methyls like that, or you can type Me2. So you will know soon that this is equivalent to this. It's simply nomenclature, or it's equivalent to that. All right. A methyl group can be represented as an Me in shorthanded notation, or simply two sticks. All right. Okay, so I'm going to now, according to the model tells me, okay, I put my diene on the top. My most electron-rich carbon should be at 6 o'clock. This will be at 6 o'clock. 6 o'clock. And my most electron-deficient carbon should be at 4 o'clock. So this guy right here on the dienophile will end up at 4 o'clock. On a watch or on a wall clock. All right. So I'm going to put now my dienophile right underneath here. Now the endo approach means that this group will be facing in. That will be folded inside of the box. So this group will go here, and so you can do it like this, or you can simply write it down. Sometimes the aldehydes are written as CHO. A CHO group means it's an aldehyde group at the end. All right. So in other words, this is equivalent to CHO. That's how it's written. All right. Now, the next thing you want to do, there's a methyl group. Notice that this methyl group stays on this side to the right. Then the next thing we're going to do is we're going to do the right approach, which means the connections. If I label these carbons as 1, 2, 3, 4, 5, and 6. Carbons 1 and 2 will connect. And carbons 4 and 3 will connect. Do you see that connection happening? Can you visualize that? You had the diene on the top and the dienophile underneath that box. Now, notice that when you started, there's this hydrogen here, and then there's two hydrogens. Let me draw that out. There's a hydrogen here, and there's two hydrogens, one here and one here, right? But we're not drawing those hydrogens right now because it'll be too crowded. All right, so we're going to keep it simple and clean. The next thing we're going to be doing is the rotation of the electrons. This is a concerted reaction. The next electronic movement happens simultaneously. So this double bond will form that sigma bond. You see that? It's going to go like that. It's going to form a bond where the dotted line in green is. And this double bond will migrate over here to form a new pi bond. And then that's going to break this. Pi bond is going to form that sigma bond. So basically you have, let me see, you have 1, 2, 3 bond breaking and 3 bond making happening simultaneously. Like that, okay? All right, and let's connect now all the dots. So I'm gonna draw now my formal box here, and this is gonna test your artistic ability. Look at that. You see that? Now we're starting to go into a cube-looking thing here, right? Good luck with your art. And so here I'll have a methoxy group there. I'll have an N-dimethyl group here. And notice what's happening here. I have an H on this side that is invisible. Now I'm going to make it visible. And I'm going to put inside here, I'm going to put my CHO group. It's kind of like on the way. Hold on a sec. Let me make this a little bit better. Out of the way, so I'll make it a little longer. That's better. CHO right there. An H here. I had a CH3 on the right side and an H on the left side. Do you see that? All right. There is an H that is going to be parallel to the dimethylamino group. And here's the thing with the other hydrogens, the ones that are internal, on the diene. Some books write it like this. You could do that, but don't do it like that. I prefer it like this. Because when we deal with bridgeheads, we'll already be forming the bridgeheads right there. So let's get used to that. All right? So that's how I would draw them. So now that is the 3D connection. And check out what's going to happen. Now I'm going to push this accordion-looking structure down. I'm going to flatten it out and draw it in 2D. So I'm going to have a double bond here. I'm a toxic group. And if I label this carbons, that'll be 1, 2, 3, 4, 5, and 6 will be there. Kind of like I was doing there in purple on the left side. And so I can label them here. So it will be 1, 2, 3, 4, 5, and 6. So keep track of your numbering. That's really important. What's going to happen to the dimethylamino group? Is it going to be up or down according to that? What do you think? That H group is down, right? That H group is really prominent. It's saying, hey, I'm up. So the dimethylamino group should be down. All right. What about the aldehyde group on carbon 2? Anything that is on the left will be down. Between carbons 2 and 3, anything that is on the left of carbon 2 and 3 is down. On carbon 4, this group right here will also be down. So anything on the right of carbon 2 and 3 will be up. So for carbon 2, my CHO group will go there. And for carbon 3, my methyl group will be up. Boy, that's thick. Oh, let's make it a little bit better, like that. That's better. That's my CH3 group. I don't need to draw CH3, but I want to. All right, so this is the endo group. All right, now notice this. This carbon was the most electron rich. Remember that? That is this carbon right here. And I'm going to label this carbon here in green, my electron deficient. It's going to end up right here in green. So on my, this is what I was trying to say. On my clock, the purple carbon ends up at 6 o'clock, and the green carbon ends up at 4 o'clock. Do you see it? And this is how I know my model to predict the Diels-Alders. It's good. All right. So basically, I'm looking at this when compared to here. When I refer to 6 p.m. or 6 o'clock and 4 o'clock, that's what I mean. All right. Okay, any questions up to this point? Notice that there was now a lot of flipping here. So the endo looked normal from the beginning here on the dieno file, and also the diene had the most electron-rich carbon at 6 p.m. already, so it was all set up right. So I need to teach you easy. So I go from easy to complex. All right. So the other thing I'm going to teach you is the exo approach. And let me tell you one more. What I'm going to do here today, we're going to try to cover all these 4 problems. These are intermolecular examples, and on Wednesday we'll do the intramolecular. So I'm going to show you how we can predict this cyclic molecules. They will make 3 rings. Let's see. No, they will make 2 rings. It will make 2 rings. This one's E and F will make 2 rings, and G and H will make also 2 rings. So this will be bicyclic molecules. G and H, on G and H, what I'm going to teach you how to do is the bridgehead Diels-Alder reactions. All right. So that's a little more complex, but we start from easy to difficult, and that's the only way I can teach this. All right. Let's do problem B. All right. So on B, one more thing before A, I forgot. Notice that this reaction is driven by heat. Without heat, this reaction will not go. So you need heat in the Diels-Alders. There are 3 components that could initiate a reaction. One is heat, the other one is light, and the third one is an initiator, usually a radical initiator. We're going to learn those for radical reactions. Right now we're learning type 4 of reactions in organic chemistry. These are the ones that I refer to as rearrangement reactions. Remember when we talked about the 5 types? This is the 4th type. And on chapter 11, radicals, we're going to learn those types. The final type, which is radical reactions. All right. So let's do B then. So notice that Your goal as a student right now is to determine, the first thing you want to do when you do the Diels-Aldrich reaction is to find that electron-rich carbon from the diene. All right? All right, so my computer is acting up weird and it's really strange today. Here we go. All right, so check this out. What is a TMS group? So a TMS group is a short for this group. So if I have a connection here, is a trimethyl silyl oxide or trimethyl silyl ether. They call that both ways. It's a silyl group with it's a silicon atom with 3 methyl groups attachments, and then the silicon is attached to the oxygen. Silicon and oxygen is a pretty strong bond in nature. So, but for simplicity, we're just gonna call it TMSO. All right. But the oxygen on the TMSO is electron rich, and so I have a question. Where do you think, where is the most electron-rich carbon? On carbon 1, or this carbon here labeled as 2? Carbon 1, exactly right. So your electronic push starts off from here, and the moment that you make a double bond there, this double bond has to break. And so we need to do a flip. We're going to flip this molecule to get it right, to get the model right. Without this flip, your problem will be wrong from the beginning. And that will be one of my answers as the wrong ones. All right, so be careful. Okay? So when I flip this, I'm going to put my TMS group here. Hold on a sec. TMSO group will be right there, representing that this carbon now is my electron-rich carbon, and it will be at 6 p.m. or 6 o'clock. All right. Now this carbon right here is fine. That will be this is my 6 o'clock. And here will be my 4 o'clock carbon. Now, since it's exo, this group needs to be switched to the right. All right, we're gonna switch that. Gonna flip that. So get your group set up the right way, and then notice that endo. When we say endo, that means internal. That's inside. That comes from Latin internal. Endo is internal or inside, and exo means external. So, and I'm going to show you in a second. So I'm going to delete this. So endo means inside. We're folding the electron withdrawal group inwards, and so the exo needs to be the opposite. So I'm going to start with my box here. And I'm going to, I didn't put enough room here for this group. So I'm going to put my TMS group right here. And I'm going to put a double bond here. Notice that the exo is going to put the amino group outside. That's what we have. All right, so I'm going to connect the dots here. I'm going to connect this carbon to this carbon here on the dieno file, and this carbon from the diene to the carbon here of the dieno file. Pretty neat. And so I'm starting to visualize my box here. I'm going to turn those electrons around. So this will form that. This moves here, and this moves here in a concerted way, just like a concert. You know, you have the director of the band moving a baton like this, little stick. And so these electrons are moving at the same pace. So here's your clarinet, here's your trombone, here is your violin. And they're moving at the same time, each one playing their own notes. All right. Okay, so I think I got rid of this bond here. There you go. All right, so now let's connect this. So I'm gonna make my box. And honestly, the Dienophile art challenge was with an intention to get you into an artistic mode, because you're gonna need it. Right here, you will need it. So OTMSO will be there. This group will be outside. This makes it exo, like that one make it endo. So now the group here that should be doing the exo doesn't do a tertiary, secondary pi overlap. In the endo, you have that. You have this carbon here interacting with this carbon here labeled as 6. That's a secondary pi overlap, pi orbital overlap. All right, so this amino group is on the right side, stays up. This H will be all the way up here. That's gonna be represented as down. There's an H here and H here. This carbon doesn't matter. That carbon is not chiral. And you have an H that goes that way and an H that goes this way. Let me fix this a little bit. I'm just gonna put the H right here so that it's not on the way. All right, and you have the 2 H's that are up. All right, so I'm gonna push this down, and I have my 6-member ring, double bond, TMSO group. This group here now is up. My amino group is up. And that's it. That's what I have there. Pretty simple molecule. All right. So, what? Yes, question. Yes, ma'am.
Why is TMSO not up or down?
A TMSO what?
Why is it not either up or down?
Oh, very good question. Excellent that you asked. I've been asked why TMSO is not up or down. The reason for that is that this carbon right here is an sp2 carbon, so it's flat. It's trigonal planar. Like if you look at this, that will be flat. You see that? This carbon is trigonal planar. Now, in the past, I've had students that have done this. And this is annoying to me. Or, oops, or this, doing this. That is annoying too, because there's no chirality there. Chirality is only for tetrahedral carbons, not for sp2 carbons. But nonetheless, that's a really good question, because every year I forget to address that. And so I'm glad that you brought it up, because that was very important to me. All right. One thing about the books will want you to memorize the following thing. They're going to say, okay, this group here, if it's endo, it will be down. This group right here, if it's exo, it will be up. Right? So the difference will be, say this was group C and D. Remember this was group C and D from our PowerPoint slides. Notice that notice this. This is why it's not good to memorize these molecules, because here it is. If you have a group like A that is on that position, it most likely will be down. But what if I told you that you have A here on this side? Then A will be up, right? From the model. Also, if I give you this instead of the C and D on the same side, then you will end up with C down and D up. So the memorization here is bad, and I don't know why the books keeps on showing it like that. Oh, memorize. This will be, the endos will be down, the exos will be up. And they always do, to get away with it, they do problems that are symmetrical. All right, like in this case, my example here was symmetrical. C and D on the one side, you end up with both down if it's endo, or both up if it's exo, because they flip. You see that? But I can give you combinations. I could give you, for the exo, what if I gave you something that ends up like that? And then you have to come up with the answer. So bottom line, this is the bottom line. You got to know how to draw these things and come up with the right answer. Because for me, let's say I want this is the answer. For me, it's simple to do this problem on my own, come up with the answer, and then simply make 3 false answers, and then you could be tripped if you don't know how to solve this, right? Because one of them could be like that, the other one could be this down and this down to make you feel, oh yeah, this is good, I got this. And then one down and one up, or it could be this up, and then this down and this down. You get it, right? And one more, I could say this down, this one up, and this one down. So I can give you several combinations, and you could get lost in the combinations, honestly, if you don't pay attention to what you're doing. So you are forced to know how to predict these things with exact precision. All right? And that's what we're going to be doing. Any questions up to this? So you know that the answer will be, in this case, if it's A, B, C, or D, the answer will be B, if I'm asking you for this particular problem. All right? But this is what I can come up with. The other thing I can come up with is I give you the final product, like the one here, the endo. Let me delete all this stuff to avoid clustering. And you simply break here, and retrosynthetically speaking, which is represented with a sort of like an arrow, a broad arrow with 2 parallel lines. You know, you're going to reorganize this. You have to have the diene, no file, will look like this, and then here's your diene. All right. So I could make the B, group B up if I put it inside. That will turn out to be up. Or if the A, I want the A to be up. I put it inside then, and that becomes a hydrogen. So that will turn into something like this instead. So you have to be careful what you are up against. All right? I'm just warning you because I want you to do well on this. And most of my students get it. I mean, 80% of the population gets it right. All right? So that's a pretty good number. All right. Any questions up to this point? You know exo, you know endo now. Anybody out there in the online section, the ones that are listening, do you have a question? All right, no questions. All right. So let me go on then, if there are no questions. Unless there's one here in the classroom. Any question? Yes, ma'am.
Can you explain the flip it?
Can I explain what?
Like when you flip it?
Yeah. Let's explain. Let me explain you how I flip it. Where? Right here. Right here, where it says flip. Okay. So when I push those electrons, I found out that carbon on the top, this one, let's call it 1, 2, 3, and 4, was the most electron rich. My job is to put that carbon at 6 o'clock south of my clock. And so then I'm going to flip it, right? I'm gonna get this molecule and flip it 180 degrees vertically, just like when you flip your pancakes, right? That's the same flip, all right? And so now carbon 1 will be here, 2, 3, and 4. You see that? It's a 180 degree flip vertically. And that helps me to find my electron-rich carbon. For the exo and on the dienophile, the problem is telling me it's exo, so I'm forced to put that amino group on the right side. So that's why I say, okay, this group has to go to the right. All right, so let's do 2 more examples here before the time is up. So I'm gonna try to finish each one in 5 minutes. All right, so here we go. My job is to find which one is the most electron-rich carbon. So I'm gonna push, right there. And when I push with this one, this complements. That one complements the pushing right there. So that carbon is the most electron-rich. It's fine where it is. So on my approach, I'm gonna keep it like it is. I don't need to flip that. My methoxy group will be out here. My N-methyl group over here. And I'm ready there. Endo, that also is ready for endo. Now this group has to be inside to the left. And so I'm going to do this. This will be a carbonyl group with an OH right there. And the methyl group will be right here. So notice that here's my 6 o'clock. And this one will be my 4 o'clock. Do you understand now the 4 and the 6 o'clock now? Got it. All right. And so I'll do the approach. I'm going to take this diene carbon and connect it to that of the dienophile. Connect this carbon with that one of the dienophile. And I'm going to make a box. And this is as beautiful as I can get it done. So, before I do that, I'll do the rearrangement. The 4 plus 2.
Dr. Odens,
Yes.
Sorry. I'm sorry if you explained the 4 o'clock and the 6 o'clock earlier. I was late coming to class, but is it always going to be 4 and 6 o'clock?
Always. Who is this, by the way?
Caitlin Harden?
Oh, Caitlin, yes. Let's go over there. So what I
I'm
meant,
sorry.
no, that's okay. I said that this connection here, my end connection, will have the electron-rich diene carbon pointed south at 6 o'clock. So it will be this guy right here. And my electron deficient carbon on the dienophile will be at roughly around 4 p.m. or 4 o'clock.
Okay.
You see that? So this bond that is right here, this bond is the same thing as this one right here, between 6 and 4 o'clock.
Okay.
You see it now?
Yeah.
Yeah, and this is my watch right here. Tick, tick, tick. Tick, 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 tick. Tick, tick.
Thank you.
You're welcome. All right. All right, so notice that I made my 2 sigma bonds right here, and my 1 pi bond is right here on the top. Then I have an NH methyl. This group is there, and I have an H right here. I also have 2 H's that are going to stick up. And there's an H this way, and there's a methyl group this way. There's an H that fulfills that carbon, and here's my carbonyl OH group, will be internal. If it is to the left, it'll be down. So I'm going to put this 6-member ring. This methoxy group is going to be what? Down, right? It's pushed down. This carbonyl group is going to be also down because it's to the left. The methyl group is up. And I'm needing this NH methyl group there. All right. Notice that in this case, this methyl group is similar to that methyl group. Just because they were to the right, that doesn't necessarily mean it's going to be the same. All right. All right. Any other question? I have 5 more minutes. I want to finish the next problem. All right. In the next problem, we're going to have a double flip. Are you seeing it? Double flip. Because now you're getting experience and say, okay, I push here and here. This will require a flip. So I will end up with my diene will look like this. This is a methoxy group. And also, my problem is an exo problem. It's asking me to do the exo, so I'm going to have to put that group to the right. Okay? So I'm going to go and get my box ready. This is the model, and if you follow this model, it'll always work. I guarantee you. So this group will be down like that, and I have a methoxy group that's coming up here. You can do the ME, or you can simply put a methyl group there. Same thing. All right. So we're getting more and more advanced as I talk to you. So make the right approach. That is the right approach. I'm starting to form my box. All right. And so I'll make now my box as pretty as I can. Double bond there. O methyl. And notice that this ketone group is to the right. There's an H inside. and this guy has an H here and another H here. There is an H that is from the double bonds right here and the two that were internal. That is my 3D connection. All right. I like the paper test. I can see the artistic side on my students with the electronic thing. You know, I lose all that. I don't know what you're drawing. So you think it would be bad? No. But yeah, some students are really good at art, and other ones are not. But there are other ones that know how to get these problems right, even in their own little art world, you know. And that just amazes me. All right, so let's do the final 2D. 2D means two-dimensional. 3D, this looks 3D, so this is like the 3D connection is three-dimensional.
What?
All right. Someone is not paying tuition. Someone is not paying tuition.
Oh.
Hold on, let me mute them all. Yeah. Okay. So, all right. So we're gonna put the double bond here, and our methyl group there. And notice that if I label these carbons as 1, 2, 3, 4, 5, and 6, I have 1, 2, 3, 4, 5, and 6. On carbon 2, I have the only chiral carbon in this problem. And it looks like that. And that is my exo product. All right. That is it. I'm gonna stop the recording. Have a wonderful day, guys.